All right. So yesterday, whether you're at home or in person, we talked about how to find some features of my graph: x-intercepts, y-intercepts, vertical asymptotes. Was that it? Just those three? So x-intercepts, y-intercepts, vertical asymptotes. So all that's great, but that's all telling me what's happening close to the origin, or towards the central location of my function. So today, what I want to talk about is what's happening at the ends of my graph. Okay, are both ends going up like a touchdown? Are both ends going down? Is it looking like our odd graph? Maybe there's some sort of horizontal asymptote. So what's going on with these graphs? Okay, so we call this the end behavior of our functions, is what we're going to call it. So what's going on? What's the end behavior? So when we talk about our rational functions, we can group them into three categories. So we can say that our functions are top-heavy. We can say that they're bottom-heavy, or we can say that they're balanced. So those are the three types of rational functions. And based on whether they're top-heavy, bottom-heavy, or balanced, we can better predict the end behavior of the function. So let's talk about top-heavy first. So what does it mean to be top-heavy? So top-heavy means the degree of the numerator is greater than the degree of the denominator. So the degree of the numerator is greater than the degree of the denominator. So let's look at an example here. So I don't know, let's try x third plus 2x plus 7 over x squared minus 7x plus 1. Okay, so first of all, how do I know that this is top-heavy? Well, I know that this is top-heavy because the degree of the top is 3, it's a third degree. The degree of the bottom is 2, second-degree polynomial. And so this is a top-heavy function. So what is the end behavior going to look like here? Well, if I have a top-heavy function, and we want to know the end behavior. So end behavior, another way of thinking about this is as x gets really, 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 really big, I'm going to plug in huge numbers for x. What's going to happen to the output values? So try to picture this here. If I plug in huge numbers for x, what's going to get bigger faster? Is the top going to get bigger faster, or is the bottom going to get bigger faster? And the answer is, because this is a third degree on the top and only a second degree on the bottom, the top is going to get bigger way faster than the bottom. So think about if you plug in like a billion. You're going to take a billion cubed plus blah, 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 and a billion squared. Well, a billion squared is still a really big number, but not nearly as close as the top there. So as I plug in huge numbers for x, the top's going to get way bigger than the bottom. Okay? So how do I figure out what's going to happen here? Well, if it's top-heavy, this is the one that takes the most thinking. What you're going to do is you're going to look at the terms that dominate. So x cubed dominates on the top, and x squared dominates on the bottom. So all this other stuff, it definitely matters. But as we plug in huge numbers for x, the terms that dominate are really the ones that are going to be most impactful to this function. So if I want to know the end behavior, so I'm going to just look at the terms that dominate, x cubed over x squared. Well, that simplifies, right? X cubed over x squared is equal to x. And so what this tells me is the end behavior of this complicated rational function is going to be the same as the end behavior as just plain old x. Well, what does plain old x look like? Well, plain old x is just my linear function that looks like that. So how would you describe this end behavior? Well, here's what we're going to write. We're going to say as x approaches infinity, what is happening to my y's? So in this, as x goes to infinity, my y is going to infinity. And then as x goes to negative infinity, what's my y value again? Well, as x goes to negative infinity, my y is going to negative infinity. And so this is what we would say our end behavior is. Our end behavior tells me what's happening as x gets really, really big, and what happens top heavy. Quick summary, we'll do one more example. You're going to look at the terms that dominate on the top and the bottom, simplify them, see if you can figure out what the end behavior of the simplified version looks like, and then that'll help dictate the end behavior of your more complex polynomial. Okay, so what's going on with this one here? So x to the fourth plus 3x plus 1, negative x squared minus 7x minus 4. So again, this is top heavy. The degree on the top is bigger than the degree on the bottom. So my strategy stays the same. I want to know what's going on at the ends of my graph. So I'm going to look at the terms that dominate. So who dominates on the top? Well, that'd be x to the fourth. Who dominates on the bottom? That'd be negative x squared. So all of these other terms, they might matter if I plug in like 3 or 4. But if I'm plugging in like 17 billion, these terms are going to be insignificant compared to my dominating terms. Okay? So I'm going to focus on x to the fourth over negative x squared. So what is x to the fourth over negative x squared reduced to? That reduces the negative x squared. So this is where knowing our parent functions comes in handy. What does negative x squared look like? That's my frowny face, upside down parabola. Okay? So what this tells me is this complicated function up here, if I threw this in a calculator, at the ends of the function is going to behave the same as my function negative x squared. So now I need to write my end behavior. So as x approaches infinity, what's your y value doing? So as x goes to infinity, that's this way. My y value is going down towards negative infinity. And as x approaches negative infinity, so as x goes negative to the left, my y value is going to negative infinity. Okay? So I think what might be helpful for you to visualize here is go ahead and take a second and graph this and see what it looks like. And don't worry about the y-intercept or the x-intercepts. Look at what the end behavior does. Okay, so I went ahead and graphed it. And it took some patience to... you can't probably see that very well. It took some patience to find the right window that I would graph this, but when I'm all done, it looks something like this on my calculator.
Students and staff.
Alright, sorry about that. But it's a complicated graph. There's a vertical asymptote. It's a weird x-intercept, weird y-intercept if you threw it in your calculator. But here's what we can predict. We can predict the end behavior. And if we look, as x goes to negative infinity, my graph's going down forever, which is what we predicted. And as x is going positive infinity, my graph's going down over here too, which is what we predicted. So just by looking at these terms that dominate and simplifying it and looking at a simplified version, it doesn't necessarily tell us what's going in here, but it tells us what's happening on the ends. It gives us the end behavior. Okay, so that was top heavy. So that's the most confusing one. So if you can hang with me, the next two are much easier to figure out. So bottom heavy, let's talk about bottom heavy. So first of all, let's define it. So bottom heavy is when the degree of the numerator, the top, is less than the degree of the denominator. Okay, so it's bottom heavy. The degree on the bottom is bigger than the degree on the top. So let's look at an example here. Alright, so let's say f of x equals x plus 7 over x squared plus 3x plus 1. Alright, so this is bottom heavy. How do I know it's bottom heavy? The degree on the top is just 1. The degree on the bottom is 2. So this is a bottom heavy function. So try to picture this. Remember, end behavior. What's happening as x gets really, 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 really big or x gets really, 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 really negative? So think about plugging in a number like 200 billion in here. If you plug in a number like 200 billion, the top's going to be equal to 200 billion plus 7. That's a pretty big number. But the bottom is going to be 200 billion squared. Whoa! Okay? So think about that. When you have a fraction, and you have a number on the top, which is, pretty big number, but the number on the bottom is just gigantic. What's going to happen as the bottom keeps getting bigger and bigger and bigger and bigger? What's going to happen overall to this function? What is this value getting close to? You have some number divided by some freaking huge number. What is a number divided by a freaking huge number? this is getting closer and closer to 0 is what's happening. Okay? So as the bottom gets bigger and bigger and bigger, this overall value is getting closer and closer to 0. Okay? Now, it's never going to be equal to 0 because the top will never be equal to 0, but it's getting closer and closer to 0. So that'll happen with any bottom-heavy function. Your end behavior is always approaching 0. Okay? So we would say as x approaches infinity, y is approaching 0. And as x approaches negative infinity, y is also approaching 0. Because whether I'm plugging in really, really negative numbers or really, really positive numbers, the overall structure of this is going to be getting closer and closer to 0. Okay? And if you remember one of your parent functions, you guys remember 1 over x? What was happening at, for the function 1 over x when we graph this? What's happening at the ends? Well, if you remember, my graph looked like this. So what's happening as x gets really, really big? Well, if you remember, this graph was approaching this horizontal asymptote at 0. And on both ends, right? So this function right here, 1 over x, is bottom heavy, right? The degree on the top is 0. The degree on the bottom is 1. And so it had this end behavior, okay? And we just kind of clued you into something else. So the end behavior, if it's approaching this value is telling me that there's a horizontal asymptote at that value. Okay? So when my end behavior is a number like 0 or 2 or 1/3, that's telling you that there's a horizontal asymptote at that value. Okay? And what is a horizontal asymptote? Well, we tend to think you can't cross an asymptote. And that's true if it's vertical, but it's not actually true if it's horizontal, and we'll look at some examples. But what I want you to think about is a horizontal asymptote is just guiding your graph. If I have a horizontal asymptote at 0, what that's doing is it's saying, okay, graph, as x gets really, really big, you're going to be approaching 0. This is just guiding you. It's a guide to show you what's going to be happening at the end. So let's summarize this. If I have a bottom-heavy function, that's telling me automatically that I have a horizontal asymptote at y equals 0. Every time. You can take it to the next. Bottom heavy, you have a horizontal asymptote at y equals 0. Okay, and then my last type of rational function is balanced. So we have top heavy, bottom heavy, now we have balanced. So balanced is what you would expect. The degree of the numerator is equal to the degree of the denominator. So the same degree. So here's an example. So 3x squared plus 7x plus 1 over x squared minus 7x plus 17. Why is this balanced? The degree on the top is 2. The degree on the bottom is 2. Okay? And again, picture what's going to happen as you start plugging in really, really big numbers in for x. So similar to when we are top heavy, we look at these terms that dominate. So these are the terms that are really going to impact my end behavior. So 3x squared over x squared. Well, how does this simplify? 3x squared over x squared. Oh, well, wait a sec. That's just 3. Okay? So with balanced, you're going to have another horizontal asymptote. And the way you're going to figure out that horizontal asymptote is you're going to look at these leading coefficients. So in this case, my leading coefficient was 3 over 1, which is equal to 3. So in this case, I'm going to have a horizontal asymptote at y equals 3. Or if you want to write our end behavior, you could say as x approaches infinity, y is approaching 3. And as x approaches negative infinity, y is approaching negative 3. Or, come on, Courage. Y is approaching 3. Okay? And if you were to graph this, I don't know what everything would look like as far as the x-intercepts and stuff, but I know that I'm going to have horizontal asymptote at 3, and as I go to the right, my graph's going to be approaching, and maybe I don't know what's going on in here, and on the left, it's going to be approaching 3, and I don't know what's going on there. But I know my end behavior, as x gets really big to the right, and as x gets really negative to the left, both are going to be approaching 3. Okay? So stay tuned for your next video. I'm doing a few examples with you.